Hello, and welcome to this talk on the wonders of semantic knowledge graphs. My name is Veronika Heimsbakk, and I'm a managing AI engineer at Capgemini, based in Oslo, Norway. I've been working with semantic technologies for the past 7 to 8 years now, and today I'm going to outreach to you why these technologies are so amazing and why you should care. So, as you probably know, the World Wide Web contains a web of linked hypertext pages. Hypertext pages linking to another hypertext page, linking to another hypertext page, and it's HTTP all over the place, representing different kinds of documents on the web. And this idea came out of a frustration that Tim Berners-Lee had while working in a lab in the mid-80s, because when scientists from all over the world met together, they brought their own physical computer with different kinds of technical implementations and hardware implementations and different kinds of data formats. So it was only impossible to share information across computers. So he imagined to exploit the internet technology that was around by providing a way to link documents and share documents across computers across the globe. So that was the World Wide Web. But imagine if you could do this with data instead, the actual data bits, the cells in your Excel sheet, the tables and rows in your SQL databases, all these different file formats. And that is what we're trying to do with semantic technologies, is to provide a kind of universal translator for all these kinds of data into a network of data containing a knowledge layer describing the semantics and meaning of the data. So there ain't any confusion on what the data actually means. There is a common understanding using this kind of universal translator. So semantics. What the heck is semantics? Well, semantics is basically, in information systems, the way data behaves and the way a machine interprets data, not humans, but machines. How could we create a unifying, uniform, universal truth for a machine to understand data? So I guess you're already thinking about JSON, right? Why don't we just use JSON to share the data and exploit the data around? Well, first of all, JSON doesn't contain any semantics, and it doesn't have any meaning for the data. It doesn't tell how the machine is going to interpret data. It doesn't state any kind of formal semantics. And I often heard that JSON is so simple. It's so easy to understand. Everybody could learn JSON and everybody can share JSON. Of course, it's easy to understand. Just take a look at this JSON file. I bet you understand what is stated here, right? Planet Earth with a moon, average orbital speed, some value, right? You can explain this data to your neighbor, to your colleague, and even to your mom. But what about this? It's the exact same information. But can you read it without having to look at the English translation of it? I don't think so, huh? And there is nothing in this data stating what planet actually is, what the Earth actually is, what the speed actually is. Where is the meaning and the knowledge in the data? And there is so much knowledge around in organizations and with you and your neighbor and your colleague and your mom. There is so much knowledge. Share it, spread the word, add knowledge to the world. So first of all, we have to name stuff. So this HTTP names for hypertext pages. They can be used for representing resources and entities. They could be used for describing planet Earth. You could have the URI of HTTP data.example.org/astronomy/Earth, and that would be the unique name for planet Earth in a dataset. Given context, state knowledge, state meaning of planet Earth. So Earth is an instance of planet. And a planet is an astronomical body. And Earth has a moon, which is called moon. Given context, describe the data using abstract concepts and reuse and share them. You can share your data with others that are working in the same domain, so they may use your knowledge to describe their own data, and you could use other people's knowledge to describe your data as well. And don't hug your databases inside an organization. Share the data. Probably not online for everyone. I know there is sensitive data as well, but inside an organization, share the data, exploit the knowledge of the total of the organization. So let's have a look at the observable universe and the difference between knowledge and data, and how knowledge and data must work together. So this kind of illustration you have probably seen before. It's a Venn diagram. You've probably seen it during your studies or some elsewhere, but here I describe the sets of astronomical objects and astronomical bodies. Astronomical objects, including several different subsets, like planetary system, and for bodies, planet, natural satellite, and star. Those are the sets we're going to have a look at today. Okay. So let's start with some abstract concepts and think about an abstract concept as a set of things. It's not one particular specific thing that you can touch, but it's an abstract set of stuff. So a planetary system, that's a concept, and that's a set containing all planetary systems. So the solar system, our solar system, where we live, is an element in the set of planetary systems. Like for planet is the set of all planets where Earth, Mars, Jupiter, Saturn, and so on is members of the set planet, and natural satellites like Moon, Phobos, Io, Titan, and so on. And then let us add the elements. So Mercury, Venus, Earth, Mars are all instances of the concept planet, and they are all members of the solar system. And the solar system is an instance of a planetary system. We have Earth and Mars having relationships to some natural satellites, Phobos and Deimos, and Moon, which are natural satellites, instances of natural satellites. And then we could add a neighbor, another planetary system, Proxima Centauri system, with a member Proxima Centauri b, which is from our point of view an exoplanet, which has all the characteristics of a planet. And now we have seen a lot of object values. So all of these things are objects that point to other stuff, right? But what about the data types and data values, like strings and numbers and such? Of course, we have them as well. So we call them literals in the world of graphs, and they operate as leaves nodes. You can't point to anything from a data value because it doesn't have any relationships going from it, but it can have many relationships going to it. So we have strings, we even have a language text strings, so we could state right in the data that Mercury is the English label for mercury, and Merkur is the Norwegian label for mercury. We could state different kinds of data types, like the aphelion for mercury is this number, AU, which is astronomical unit. And astronomical unit is a unit defined in some other data set. So here I'm reusing the knowledge of others. That's quite nice, eh? So you don't have to invent the wheel again. So if you're working with a domain which are widely spread and big domain like life sciences, for example, you bet you will find a lot of vocabularies and data already that you could use and reuse and to its full potential when describing your own data. So we want the shared data models. So as I mentioned before, the World Wide Web saw the light of day in the late 80s and followed by HTTP, HTML, and these standards that began on the World Wide Web in the early days. And in 94, the World Wide Web Consortium, W3C, was established. And their purpose is to be like an organ to orchestrate the different kinds of standards around the World Wide Web, and of those being the semantic web technologies as well, like RDF, which is the fundament of all semantic technologies. RDF stands for Resource Description Framework, and if you don't know it, you will. You will hear about it, and you will have a look at it, okay? Because you're thinking in graph already, and I'm going to show you how. So the standards are found at W3C's homepage. So please go have a look at them. So here is some data again. So have a look at the element Mars in the set of all planets. It's a member of the solar system, which is a planetary system, which is an astronomical object. Planet is an astronomical body, the same for natural satellite, and Phobos and Deimos are both natural satellites, and we have some data connected to Mars, so data values. So abstract concepts, that is the knowledge layer of the data, right? Abstract concepts are the meaning of the data and the knowledge in the data model, while the instance data are the actual data stored in your databases, like Excel sheets, SQL databases, and whatever that you possess. So abstract concepts, knowledge and meaning, instance data, the actual data. So I want you to talk about data and the meaning of data. And thinking about data as a graph is quite intuitive and natural. I bet when you try to explain a concept for a colleague or a client, you often go to the drawing board, right? Drawing boxes and arrows on the whiteboard, trying to explain stuff, trying to explain the business model, trying to explain the architecture of the system, trying to explain whatever concept or domain. Well, so you're already thinking in graph. It's quite natural to think in graph, but still we force data into tables. Why? It's so unnecessary when we could let data flourish in their natural way of connectivity, right? Just try it. And accessible semantics, this knowledge layer, combined with a graph-based representation, creates so much value. And RDF being designed for data exchange, and when we're being able to share the knowledge of data, we need to talk about knowledge, we need to move from data to knowledge. I've experienced so many times that people talk about data and people talk about domain expertise, and they have like 15 different definitions for the same term. We can fix this with knowledge layer, right? making every person in the organization talking about the same stuff. And no, it's not SQL I'm talking about. It's of course semantic knowledge graphs. And an example of stuff you can do and represent in a semantic knowledge graphs is things like this. It's somewhere between propositional logic and first order logic. So stuff like all planets are astronomical bodies, that's an easy one. That's the subclass relationship, right? It's inheritance. And you can state it directly in the data as a triple, as a connection. Planet, subclass of astronomical body. Nothing is both a planet and a star. That is also possible to express with graph data. A planetary system is something that has a star at center and planet as member. That is also perfectly fine to state in a semantic knowledge graph. And what the graph will do is to add information. And we're going to have a look at an example of that later, but these are restrictions that we give to certain concepts in the graph. And when we run that through a reasoner will add data to the graph, creating new information, new knowledge, and potentially discover new insights in already existing data. That's quite cool. Okay, so what I want is the open source and open data communities to share their knowledge across the web. So we already have good shared definitions of basic things, but we always need more knowledge. There is a lot of knowledge out there. Please share it. So we have stuff like Dublin Core for publications, widely used in libraries and academic purposes around the globe. We have for human relations, friend of a friend, we have financial ontologies that I know nothing about, but if I ever happen to be with a client in the financial sector, I know where to go and know where to find knowledge and common terminology for that particular domain. We have units of measure, quantity, kinds, dimension, and data types, QDT, which is one of my favorites, describing all kinds of units you can think of. Like, for example, the astronomical units that I showed in the graph for planets comes from this vocabulary, and its definition of astronomical unit is found there. So move from data to knowledge. And there are many more open data sources you could use to expand, enrich, and describe your data with. So we see here a snapshot of the linked Open Data Cloud from May last year. And we see the red blob on top, it's life sciences, widely used and a lot of knowledge to be shared there. We also have linguistics, the green ones. We have public sector and government, the yellow ones. We have media, the purple ones, and geography, publications, social networking, and other kinds of stuff. So there is a lot of information out there on the web waiting to be reused by you and waiting to be enriched by you. So, okay, I know what you're thinking. Semantic Web, seriously? Yeah. You probably heard about the Semantic Web before. It's been around for 25 years. And yes, seriously, we have been doing this for quite some time, and you need to pay attention. Actually, it works. And we have a lot of success stories with the computational power of today's machine and doing this kind of reasoning problems and doing validation problems. And we have amazing query plans doing data exchange, opening data in organizations and opening data to the web, sharing knowledge, sharing information. So yes, you should pay attention. I want to share my references before I go on to the demo. So the demonstration want to briefly take you through this since I'm not clocking my time, so I don't know how much time I've spent. So let's have a look at the stars, and let's have a look at planets. So I'll start with the planets, I think, since that's the easiest one. So here I have some concepts: astronomical object containing planetary system, an astronomical body containing natural satellite, and dwarf planet, planet, and star. So we see here in planetary system, we have a restriction saying that a planetary system is something that has a member, some planet. So a planetary system has planets as members. And I have two instances of planetary system, which is the Proxima Centauri system and the solar system. And the solar system, let's have a look at that one, contains the members of the solar system, even Pluto, which is a dwarf planet. So that's our planets. Let's have a look at the stars. So the stars contains of the classifications of stars. And if you're not familiar with them, I can briefly explain that these are different kinds of stars that you can find in the universe. And I have a quite simple definition. I know there is a lot more that defines these classes, but I chose to go with the Kelvin temperature of stars, the O-type star being the supergiant stars, which are the largest category, down to the M-type star, which is small red dwarfs, having a much colder Kelvin temperature. So you see here that the rules are defined in ranges of Kelvin temperature. And I've also added some stars here with different kinds of Kelvin temperatures. So if I now turn on the reasoner will add information to my existing data to fulfill the restrictions set. So for the K-type star, which is stars in the range, Kelvin range, stated in this restriction, it will add information to fulfill those restrictions. So if I start reasoner, you could see that the reasoner reasoned that these K-type stars are subclass of stars, and it has one instance, which is Epsilon Eridani. And if we have a look at that star, we see that the Kelvin temperature is 5084, and it's reasoned as a K-type star, which is correct since it's falls in this range. And the same for the other kinds of stars here. So behind the scenes here, the reasoner added information to my existing graph, fulfilling the restrictions. So I gain new information in this process. Because before reasoning, Epsilon Eridani wasn't a K-type star, it was only a star, but because of the Kelvin temperature and the restrictions set for K-type star, the reasoner discovered that Epsilon Eridani was a K-type star. Okay, so let's merge these data files, both planets and stars, and see what we can find out. So I'll start reasoner and we'll go through searching for stuff. So I'll start with the natural satellite. And we see that Phobos is a reasoned information for natural satellites. And if I go to Phobos, I see that Phobos doesn't contain any information, but it's reasoned as natural satellite because Mars has a relationship to Phobos, and the relationship Moon expects a natural satellite in object position. So therefore, the reasoner understood that Phobos has to be a natural satellite and added that information for me. We have the stars again that we saw in the last example. Planetary system. Here we have a new planetary system. we have the Canopus system. So I'm going to have a look at the Canopus system. Reason to be a planetary system because it has a member, which is a planet. And Arrakis is a fantasy planet, which is the actual name for the planet Dune. Frank Hubert, he wrote Arrakis as the third planet surrounding the Canopus star, which is an actual star in the universe, an F-type star to be exact. And Canopus is the center of the Canopus system, and one of the planets is Arrakis. Even though Arrakis is a fantasy planet, it's reason to be an astronomical body because of the relationship here. And that's quite cool. Yes, and that was it for the recent stuff. I will publish this data on my GitHub, and also writing a README on how to use the reasoner and how to add new information in this program called Protege. So you could start exploring graph data on your own. And behind the scenes here, the data looks like this. We have subjects, predicates, and objects. So we see here that Neptune is a type of planet. And we see that Pluto has a moon, Styx, and so on and so on. So with a tiny bit of effort, you can read this syntax quite easily. It's not a big hassle at all. My client can do it, and they are all old sailors, all of them. So go for it. And remember, yes, seriously, Semantic Web and semantic knowledge graphs. We have been doing this for some time, and you need to pay attention. Thank you so much for listening to me, and please reach out if you have any questions or comments. Thank you.